Welcome to this video on convolutional neural networks in deep learning. In this video, we'll be looking at convolutional neural networks from the point of view of their architecture, the types of layers that these networks have, and the operations involved in each of these layers. And we'll also be listing out a few applications of convolutional neural networks. So, what exactly are convolutional neural networks? So, basically, convolutional neural networks are a class of neural networks which are commonly used for uh, analyzing visual imagery. So basically, in the field of computer vision, a lot of research has been done using convolutional neural networks. So a very general application of convolutional neural networks is image classification, and a lot of research has been carried out in this field. For example, we can take classification of emotions as an example. Not only emotions, so emotions can be captured via faces of people. So not only emotions, all different kinds of objects can be classified using convolutional neural networks, and the difference between these networks and the traditional artificial neural networks that are there is that in these networks there is no explicit um, feature processing which is actually added at the beginning. So there's no feature extraction which is done at the beginning of the network for the data. In fact, all feature extraction is done within the body of this network. So that is the idea behind convolutional neural networks, which we'll be discussing in much more detail a little later. Now, whenever we are talking about images, the starting point of building a neural network is we have to look at the image from the point of view of its representation. So, what is the digital representation of this image? So, when we talk about the image representation, so we consider the two different types of images, the black and white, the grayscale images, and the color images. We can represent a black and white or a grayscale image using a 2D array representation. So basically each pixel in the image will correspond to a corresponding uh, location in the 2D array. So it will be following the same image itself, and each pixel will have an intensity of between 0 to 255. So that is the idea. So it will be a 2D array, and if you're going for a colored image, then the representation will have the same 2D array replicated among three different channels. So for example, pixel 1 in this image, colored image, will have a representation in the uh, red channel, in the green channel, as well as the blue channel. So pixel 1 will have some intensity value in the red, green and blue channels respectively. So it becomes a 3D array representation. So it's a three-dimensional representation when we talk about a colored image. So that is it about the image representation. Now that we know how we are representing our data for convolutional neural networks, let us talk about the layers that are there in a convolutional neural network. So, there are three different types of layers in a convolutional neural network. The convolution layers, the pooling layers, and the fully connected layers. We'll be looking at each of these layers when we see the entire architecture. So before we talk about each of these layers, we will look at a very fundamental operation which happens inside a CNN, uh, that is known as convolution, as the name comes from that operation itself. So we will just have a look at that operation. And that operation is very similar to what we have studied in the field of signal processing or image processing, where actually we use something which is known as an image kernel or an image filter. So filters or kernels or feature detectors all mean the same. So what are these? These are actually nothing but a small matrix which is applied to an entire image. So for example, we have come across these in image processing, like you want to have some kind of blurring, so you have a blur filter. So you want to blur the image a bit, so you have a blur filter. So in case of the convolution neural networks, these filters are referred to as convolution kernels. So the term for them here is convolution kernels. Uh, Once we pass them over an image, it is known as convolution. So the process of passing them over an image one by one, so we need to keep on shifting the kernel one by one to perform the convolution operation. So that process of passing is known as convolution. So examples of the filter. So for this Taj Mahal, there are different filters. So this is the the sharpen filter which we can see here. So it's a 2D matrix of some values, some integer values, so which is applied over the original image to get a sharpened image. Similarly, this the second one that we see here, this one is the blurring effect. So you can see the blurring effect on the Taj Mahal. This is a blur filter. So likewise, you have different kinds of filters, which are the fundamental blocks, we can say, for the convolution operation. So how does this work actually? So suppose we have this kind of an image. So let us consider these intensity values normalized between -1. So three values are possible: 0, 1, and -1. Suppose these are the values, just for an example. And you have this kind of a filter. So it's a 3 by 3 filter. How do we perform this operation? So to perform this operation, you simply take the filter and place it on the top left corner. So once you place it on the top left corner, you multiply the respective uh, values in the of the pixels or respective intensity values of the pixels with the values of the filter. So these are known as filter weights. So multiply these intensity values by the filter weights. Once you multiply each of these values, you sum up the result. So after multiplication of the respective values, you will get this kind of a result actually. So 0 multiplied by 0 gives you a 0, 0 by 0, 0. 1 with -1 gives you a -1. So for each of the pixels of this original image, you will be getting a new value after multiplying by the filter weights. And once you get this result, you sum up these values. So once you sum this up, the answer is -1 plus 1 plus 1 plus 1, which is nothing but 2. So the result is 2. So this is the result of one convolution by the filter. This is the operation, and this operation has to be repeated over the entire image by sliding this filter one to the right, one or more steps to the right, and then uh, across the columns as well. So across the rows as well. So across the columns, you slide it towards the right and slide it down as well. And that is how you get the final convolved image. A new image which represents the convolution operation. So let us see how we use this particular convolution operation in the context of a CNN. So let us see this example. So assume that our input image is 7 by 7 in size. So Just for simplicity, let us not assume it is an RGB image. Let us assume a simple grayscale image which is having a single channel. So we are talking about an image, uh, grayscale image. So its representation is a 2D matrix representation. And consider this filter of size 3 by 3. So given this, if we are to perform convolution, then we simply place the filter over the image, perform the convolution operation, and slide the filter along the image with what is known as a stride. So we make use of a stride here. This stride can vary by different values. So if, for example, in this case, the stride value is 1. That means we are moving the filter one row at a time or one column at a time. So that is a filter convolution operation with stride 1. So if we move this filter one by one with stride 1, then this is the first stride that the filter has taken. You perform convolution. Again you perform the convolution with the next stride, and so on till we reach the end of this image. So the output, resultant output. So this is done column wise, along the columns. This will also be done row wise. So once we reach the end of this, we will shift this block here, filter here. So it will be covering this area. Next, after we are done with this sliding towards the right, we will slide towards the rows. So slide one down, and then again this row. Then we'll be looking at uh, this set of pixels, these set of pixels, and so on, move towards the right. So performing these operations, the output that we get from this kind of an operation will be 5 by 5 output. So because for the first convolution operation, that is this first thing, you will get one value. For the second, when the stride uh, is at the first stride has been taken by the filter, you will get one value, second value, then third, then fourth, and then fifth, and then you have reached the end. So this row wise you have 5, similarly column wise also you have 5. So 5 by 5 is the output after convolution. So you get a 5 by 5 2D matrix after applying convolution with a stride of 1 to a 7 by 7 image. So basically this convolution operation makes the image smaller. So what we have done is, from a larger image, if you apply the convolution, you take the strides, it will make it smaller. So stride of 1 makes it smaller, stride of 2 will make it even more smaller. So as this, you can see in this diagram, is this is the input image, this is the filter or the feature detector. So what is the output of this? That output is nothing but a feature map. The output that you get out of this image after applying the feature detector is a feature map. So now you are with your feature map. So actually we create, in the process of convolutional neural network, in when we use convolutions, we create multiple feature maps that we'll see shortly. So instead of a single feature detector, you have multiple such feature detectors which are present at each layer of the network. Now let us see what happens when the stride is 2. So when the stride is 2, the same example that we had, 3 by 3 filter with 7 by 7 image. So initially we are placing it here. Next time we take a stride of 2 to the right. So we got one convolved value. Now we have got the second value after performing convolution, and then we get the third value. So the output of this operation will be 3 by 3. So when the stride is 2, the output will be 3 by 3. So with this, now we have got an idea of what could be the possible formula for getting the output dimensions after applying this convolution operation. So let us generalize it to a formula. So if our image is n by n, the dimensions of our image is n by n, and the dimensions of the filter is f by f, then the formula for getting the output is n minus f divided by s, the stride, plus 1, if s is the stride. So for example, if n is 7 and f is 3, if the stride value is 1, then the resultant image, that is the resultant feature map that we will get, will have 7 minus 3, n minus f, that is 7 minus 3 divided by 1, 1 is the stride, that is 4 plus 1. So the resultant will be 5 by 5. This particular example we have already seen. Now for when the stride is 2, the value that we get will be 3 by 3. The output that we will get will be 3 by 3. And when the stride is 3, then it is not possible. So we cannot go for a stride of 3 because you're not getting a whole number here. So that is the generic formula. So this formula is very important. The generic formula for computing the output that we'll get after applying convolution. The next concept that is involved while designing convolutional neural networks is the concept of padding. So generally when we apply convolution, so before applying convolutions, we perform what is known as padding to the original image. So we pad the original image along the borders with zeros. So as seen in this diagram, so this image, original input image was 7 by 7, and after padding we got an image of 9 by 9. So it will be along the width and along the height of this image, padding will be applied, so the resultant image will now be 9 by 9. Now on this padded image, if we apply the convolution operation with a stride of 1, the same example, so the input image initially was 7 by 7, but now it has padding applied to it. So what is the size of the output? What is the dimension of the output? So using the same formula which we had seen earlier, only thing is the size of the image has now changed. We get the resultant to be 7 by 7. So what we get is, so n in this case is 9 and f is 3. So 9 minus 3 is 6 by s, that is 1, plus 1, that is 7. So if we apply padding to the image, then we can preserve the dimensions of the image even after convolutions uh, if we have a stride of 1 in this case. So it is very common to see convolution layers with a stride of 1, filters of size f by f, and 0 padding with f minus 1 by 2. So this is going to preserve the size of the image spatially. So the resultant that you will get after convolution, if you use padding, will be the same image. So the dimensions basically of the image will remain the same. So if the filter size is 3 and you pad the image with 1, and if the filter size is 3, you need to 0 pad it with 2. If it is 7, then you need to 0 pad it with 3, so that the image dimensions remain intact after performing convolutions. Now let us see how we can perform convolutions on RGB images. So we have already seen the grayscale version of it. So when we have an RGB image with us, then in that case, there are three different channels, red, green and blue. And taking this example which is there on this slide, so our image is having a dimension of 6 by 6 and our filter size is 3 by 3. And since we have this uh, image as an RGB image. So there will be three channels. So that is why it is the input dimension is 6 by 6 by 3, and the filters also we'll be having 3 by 3 by 3 filters for the three different channels. So one filter will be for the R channel, the second one will be for the green channel, and the final filter will be for the blue channel. Now once we have this set, um, the resultant, if you see here, is a 4 by 4 output that we get. So when we apply one convolution filter over this image, the result is 4 by 4. So how do we arrive at this 4 by 4 image? So let us view this as a three-dimensional filter. So because the third dimension, this dimension, is basically nothing but the channels. So there are three channels, that is why we require three filters. So now this becomes a 3D filter. So it becomes something like this. So this is a 3D filter, the same filter we are visualizing it here. So we apply this 3D filter over the image. So how do you apply it? So you perform the same operation, that is you do the multiplications of each of these values, so these weights with the pixel values. For the red channel, you do that multiplication. The second filter you take, you apply it on the green channel, and the third channel filter you take, you apply it on the blue channel, and you perform those multiplications. Once you perform those multiplications, you will get how many values? You will get uh, 27 such values. So you'll get 27 such values. You add them 3 by 3 by 3, that is 27. So you add them up and you get one value, and that value will be this value. Similarly, you do the same thing for the next block when you take a stride of 1. So again the same operations, 27 values, you will get the second value, this value. This keeps on continuing till you get all the values. So the resultant of this will still be a 2D value, 2D image that we get of reduced dimensions, that is 4 by 4. So we'll be using the same formula. The formula will be n minus f, that is 6 minus 3 in this case, divided by stride, in this case it is 1. That is the result is 3 plus 1, that is 4. So 4 by 4 will be the output. So that is how we apply convolutions on RGB images. The next concept here is that we have already seen what a convolution is for a 2D image, and then that is a grayscale image basically, and then the RGB variant as well. So we have visualized it as a 3D um, uh, operation that is performed on those RGB images. So now in practice what happens is you do not have a single such filter which is applied, but you have n number of filters in a layer. So if you consider a convolutional layer, so in that you will have n number of filters. Each of these filters will do the task of identifying specific features or detecting specific features from the image. So for example, in this particular example, one could be a horizontal edge detector, and another could be, this filter could be a horizontal edge detector, and this filter could be a vertical edge detector. So you can have n number of filters which are applied in a convolutional network. So the result of all this you get, so you will get 4 by 4 such filters uh, for results for each of these filters. So if you have like 10 filters here, you will have 10 such 4 by 4 outputs. So what we do is the final output of this layer then will be a stacking of all these outputs that we have got together. So 4 by 4 stacked by followed by a 4 by 4 output. So since here there are two filters, the resultant output would be 4 by 4 by 2. If there are 10 such filters, the resultant output would be 4 by 4 by 10. So let us see this example. So considering the input volume to be 32 by 32 by 3, if we are given with 10 5 by 5 filters with stride 1 and padding as 2, what would be the volume size? So the formula for finding out volume is you have to consider the pad as well as the stride length. So it will be uh, the original input dimensions, that is 32, plus twice of the padding length minus the filter length, filter dimension length, that is 5, divided by the stride, that is 1, and you add 1 to it. So basically it will be 32. So 32 by 32 spatially. And what about the height, volume, the third dimension? The third dimension will be equal to the number of filters which I use, that is 32 by 32 by 10. So the resultant volume will be 32 by 32 by 10. So if we have to coin a general formula for this, if I have an n by n by c input, where n is the dimensions, the size of the input, and c is the number of channels in the input, and if I have an f by f filter, and s is my stride, k is the number of filters, and p is the pad length, then the general formula for finding the output dimensions would be n plus 2 times p, the pad length, minus f, the whole divided by s, plus 1. So this will be repeated from the for the length and breadth, times the number of filters. So it will be 32 by 32 by 10, because there were 10 such filters. So this is a very important formula that we should remember, which gives us the output volume. Now that we have done this detailed discussion on convolution operation as well as the convolution operation on an RGB image, let us see what exactly is one convolutional layer of a CNN. So continuing our same example, we had a 6 by 6 by 3 image input which was RGB, and we had two different filters, each of 3 by 3 by 3. So what happens in a convolutional layer is, after this there is some non-linearity which is applied. So this is a linear operation which is performed, convolution, which it's a linear operation. Then we apply the activation function, some activation function which is non-linear. So for example, ReLU is a very common activation function which is applied in convolutional layers. So you apply ReLU, so you have some bias added, and to this 4 by 4 resultant. So when you apply this convolution, you will get a 4 by 4 image for the first filter, or 4 by 4 image for the second filter. And what you do is, you add the bias to it, and you perform a ReLU operation, ReLU on this. So when you perform this ReLU operation on this, the resultant will again be a 4 by 4 value. So a 4 by 4 image is what you get as output after you perform ReLU. Once this ReLU is applied, so you get a non-linear output of this, which is again 4 by 4 dimension. So for the first filter and for the second filter. And what we do is we stack this together actually, rather than what I had shown earlier. So it is not that directly whatever is got is stacked, but a nonlinear activation function is applied and then it is stacked. So the resultant will be 4 by 4 by 2. And this is what is exactly one convolutional layer. So it is a convolution operation followed by a non-linear activation function which is applied over the convolution operation, which actually forms one convolutional layer. So this is what is one convolutional layer. Now since this is a neural network, so we always talk about neural network in terms of activation functions, we talk in terms of activations, inputs and the weights. So as I already told you, these filters that we are using, these are nothing but the weights of the neural networks. So let us see what exactly we mean by that. So the number of parameters or the weights for this particular convolutional layer can be computed easily. So if our input volume is 32 by 32 by 3 and we have the same example, that is 10 5 by 5 filters with stride 1 and pad 2, the question is, what is the number of parameters of this layer? So in this case, each of the filter values that we have are the weights, are nothing but the weights. And what we are doing is we are multiplying it with the inputs. So W times X, the input, plus the bias is what we are doing. That operation we are performing. So the number of parameters that are there is nothing but the filter, the filters are the weights. So there are 5 by 5 filters in this example. So 5 by 5, 25, but 25 across 3 dimensions for the 3 channels. So 25 into 3 weights plus 1 bias. So total parameters for this particular example, this layer is 76 parameters. So 75 plus 1 for the bias. So these are the total number of parameters that are there. So even if we see in the last example, uh, whatever we are getting, whatever filters we are using, like 3 by 3 by 3 are the number of parameters for each filter. So for this first filter, you have 27 parameters plus 1 for the bias. So total 28 parameters, and since there are two such filters, you multiply it with 2. So you have total 56 parameters. So in this case, in this second example, which we were just discussing, there are 10 such filters. So each filter is having 76 parameters. So 10 such filters will have 76 into 10, that is 760 parameters. So this is the formula for computing the number of parameters given a filter and the number of filters. So it is nothing but F cross F cross C. So F by F times C. C is the number of channels plus 1, 1 for the bias. That will be the number of parameters for each filter times it will be K for K filters. So the total number of parameters is given by this formula. The next building block of a convolutional neural network is a pooling layer. So the CNNs do not have only convolutional layers, but they also have pooling layers after each convolutional layer. So what do we understand by this pooling layer? So basically, a pooling layer makes the representations uh, formed by the convolutional layer smaller and more manageable. So they basically help to reduce the computation time of a neural network by reducing the representation size, and they operate over each channel independently. So they are performed channel wise at each layer. So if n number of channels are there for a previous input to this pooling layer, they will the kind of operation which is performed for this layer, it operates on each channel independently. So basically, if this is the block, this is a block of input which is given to a pooling layer. So it reduces the dimensions of that block specially, but um, the number of channels are preserved because it is done channel wise per channel. So let us see what pooling is. So a very common pooling technique is max pooling, although there is another like known as average pooling as well. So but this is the more commonly used variant of pooling. So what happens in max pooling is, again you have a filter, and that filter you apply to regions of the image. So this is your 2D image. So what you do is, since you're doing it channel wise, so separately, so if there are 3 channels, so for each channel you will be doing the max pooling. So you divide that image into sections, and within that section you find out which is the maximum value. So for example, if there's a 2 by 2 filter for max pooling, so you divide this image into 2 by 2 sections. So 2 by 2, 2 by 2, and so on. So for each section that we have taken, and the stride here in this case is 2. Stride is 1, then again you have to find the max of this and then write out. So the resultant will be max you find out among all these 4 values, that is 6 in this case, and you write here. Next you find again max among these 4 values, write it here, and so on and so forth. So this is the max pooling operation. So let us take an example. So if it is a 7 by 7 input and a 3 by 3 pooling that is applied with a stride of 1. So use the same formula. We use the same formula that we have used earlier for convolutions, that is n minus f divided by stride plus 1. So here we do not perform padding as such. It's not very common to perform zero padding before you apply max pooling operation. So if at all we apply padding, then it will be n plus 2p minus f. The same formula we are going to use. So the resultant will be 5 by 5. But this 5 by 5 you will get for all the number of channels. For each channel you will get a 5 by 5 output. If 3 by 3 pooling is applied with a stride of 2, then in that case the resultant output using that formula will be 3 by 3. So what is the general formula for the output shape after we apply pooling? So given that the input dimensions are W1 cross H1 cross D1 for the pooling layer, and if F is the pooling dimension and S is the stride, then the resultant output is W2 cross H2 cross D2, where what is W2? W2 is nothing but W1 minus F divided by S plus 1, the same old formula that we have. What is the H2? H2 is again the same formula, H1 minus F divided by S plus 1. And D2 is the same as D1. So that remains unchanged. The number of channels remains unchanged. So why do we not go for ANNs for this kind why should we not go for ANs for image classification or image related tasks? Is because in case of ANNs, the number of parameters will increase rapidly because of the kind of representations that we have there, because everything there is flattened. You do not have a 2D representation at all, so everything is flattened out. So because it is flattened down, so if you have something like a 32 by 32 by 3 image that you have RGB image, so imagine, so just let us approximate it, 30 by 30 cross 3, so it will be like 30 by 30 itself is 900 cross 3, that means 2700 parameters will be there for that single image uh, for connecting it to one single neuron, for finding a single computation, single activation. And imagine that will be done for all the neurons in that layer. On the other hand, we have already computed the number of parameters for the convolution operation. It is very less as compared to that. For the same example, 32 by 30 by 3, it is simply 280 parameters for those 10 filters that we had. Sorry, 760 parameters. So this you can see the number of parameters decreases drastically if we use CNNs. So also 2D information is lost as we are going to flatten the image, and these networks work well only on similar well-centered images and not on any type of images. So if the image is shifted in some other picture, then in that case it will not work as well. So on the other hand, CNNs are fault tolerant in that case. So the advantages of CNNs are they use convolutional layers for alleviating all these issues, and you have this concept of filters. They reduce the number of parameters. They look at local connectivity. Everything is not fully connected. Only the final few layers are fully connected layers. So we have so far seen the two building blocks of CNNs. Apart from that, you have final layers which are fully connected layers. So let us see how it looks like with an example. So this is for an image classification. So where you have like these 4 to 5 classes which are given here. So you will have a series of convolution ReLU, and then pool layers in between. So series of sequence of these layers you will have, and the final layers will be whatever output you're getting will be flattened out. So that final image that you will get will be flattened out into a single flattened vector, and then you will have your feed forward network coming ahead, and final layer will be a softmax layer for getting the final classes. So that is the architecture of a CNN. So this is a typical architecture. What happens in a CNN? So you have uh, convolution followed by pooling, followed by convolution, followed by pooling, and so on and so forth. The final layer is a flattened layer. After the last layer of pooling, you will have a flattened layer where you will take all the activations and just stack them up together into a vector, and then you can have one or more hidden layers after that which are fully connected. So this part of the network is fully connected, and then finally you have your uh, classification layer, the final layer, which is the softmax layer, depending on the number of classes. It could be softmax or sigmoid depending on the number of classes. If it exceeds 2, it's going to be softmax. If it is less than 2, it can be sigmoid. And what you see here is what basically each layer is doing. So basically the idea is, as layer by layer, as we are progressing layer by layer, the convolutional neural network actually tries to break the image down into parts. So first of all, the very low level features like edges are detected by the model, and then these low level features are combined step by step in the further layers. So then in the next layer you can see that there's a texture that is being identified. Then this texture in the next layer, these textures are combined together to view object parts, and then finally the last layer will finally be able to identify the object as a whole. So that is the idea behind these filters at each layer, and these filters are actually trainable parameters, so they are learning. So we are not saying that okay, we have 10 filters and one is a edge detector, one is curve detector, or horizontal edge, vertical edge, whatever it is. We are not defining that. The network itself learns to define what it has to learn. So it decides what it has to learn as learning progresses. So that is the beauty of CNNs. You are not telling anything, you're just giving the image across those 3 channels. That's it. You're not doing any kind of feature extraction. So that is the beauty of CNNs. And it makes life much simpler by just performing these two mathematical operations, that is convolutions and pooling. When we talk about the applications of convolutional neural networks, there are many applications. Some of them are listed here. Semantic image segmentation is one such application where you are actually segmenting the image into different parts. to identify different objects from the image, some meaningful objects from the image. Then, of course, the autonomous driving is also one application where object detection has to be done. So computer vision, basically, all the applications which are under the umbrella of computer vision can be solved using convolutional neural networks. And this is an application of image colorization which can be done, and visual translation. So all these are some applications of convolutional neural networks where maybe not entirely the convolutional neural network is used, but in parts of the entire architecture it will be used for identifying the features of uh, what make an image. So for recognizing images, basically, in any application that you have, CNNs will be used, and then that can be used as part of a larger application. So that's it about this discussion on CNN. Thank you.